In this module, you will study about work, energy, and power. Learning objectives. Energy. Energy transfer and conservation of energy. Work and power. Driving and car safety. Energy is the capacity to do work. There are different forms of energy. We will look at chemical energy, potential energy, kinetic energy, electrical energy, heat energy, light energy, nuclear energy, and sound energy. Chemical energy. Chemical energy is the energy of chemical substances that is released when they undergo a chemical reaction and transform into other substances. Some examples of storage media of chemical energy includes batteries, food, gasoline, and oxygen gas. During the lifetime of plants and animals, plants absorb energy from the sun. If it is deeply buried in soil and if there is no microorganisms to act on it, then under temperature and pressure, it will convert into petroleum and coal. The energy stored in the petroleum products and coal is released when we use these fuels. The energy stored in food is stored in human body or animal body, which is released when we do some work. Potential energy. Potential energy is the energy possessed by a body due to its state or condition or due to its height from the surface of Earth. So this is the energy a body has because of its position or condition. A body above the Earth's surface, like water in a mountain reservoir, has potential energy stored in the form of gravitational potential energy. To lift a body of mass m through a vertical height h at a place where the Earth's gravitational field strength is g needs a force equal and opposite to the weight mg of the body. Hence, work done by force equals force into vertical height, that is mgh. So the mathematical expression for potential energy is mgh. Elastic potential energy. Work has to be done to compress or stretch a spring or elastic material, and energy is transferred to potential energy. The potential energy is stored in the form of strain energy or elastic potential energy. A spring in its normal state is not possessing any potential energy, but if you compress or stretch, then potential energy will store in the spring. Elastic potential energy developed in a spring due to an extension of length x is given by U equals half kx square, where U is the elastic energy, k is spring constant, and x is the change in length or change in position. Kinetic energy. Kinetic energy is the energy possessed by a moving body. A person walking, a thrown baseball, a box falling from a table, and a charged particle in an electric field are all examples of kinetic energy at work. Kinetic energy depends upon two factors, the mass of the object and velocity. For a body of mass m traveling with velocity v, the kinetic energy is given by Ek is equal to half mv square. Electrical energy. Electrical energy is a type of kinetic energy caused by moving electric charges. The amount of energy depends on the speed of the charges. The faster they move, the more electrical energy they carry. Heat energy. This is also called thermal or internal energy and is the final fate of other forms of energy. It is transferred by conduction, convection, or radiation. Thermal energy is defined as the total of vibrational, rotational, and translational kinetic energies of atoms, ions, and molecules. Light energy. Light is a form of energy which our sense of sight can detect. Light is electromagnetic radiation and travels in a straight path. Nuclear energy. Nuclear power is the use of nuclear reactions to produce electricity. Nuclear power can be obtained from nuclear fission, nuclear decay, and nuclear fusion reactions. Presently, the vast majority of electricity from nuclear power is produced by nuclear fission of uranium and plutonium in nuclear power plants. Usually, boron or cadmium rods are used as control rods. If we insert these control rods into the nuclear reactor core, it will slow down the nuclear reaction. The energy produced from the nuclear reactor is used to boil water. The steam power is used to rotate turbines to produce electricity. Sound energy. Sound is the movement of energy through a substance like air or water and is caused by vibrations. Solids, liquids, and gases transmit sound as waves. Energy transfer and conservation of energy. Law of conservation of energy. Energy cannot be created or destroyed. It is always conserved. However, energy is continuously being transferred from one form to another. Ultimately, all energy transfers result in the surroundings being heated and the energy is wasted. The lost energy is often converted into non-useful heat. A device is efficient if it transfers energy mainly to useful forms and the lost energy is small. You can see some examples of energy transfer and efficiency during that transfer. Electrical motor, for example, 90% efficiency is there and electrical energy is converting into kinetic energy. And similarly, you can see different forms of energy conversion in electric generator, gas boiler, fluorescent lamp, turbine, car engine, and filament lamp. Kinetic energy and potential energy during motion, during free fall and during the bouncing of balls. A mass m at height h above the ground has potential energy mgh. During free fall, its velocity increases and it gains kinetic energy. If air resistance is negligible, its kinetic energy on reaching the ground equals the potential energy lost by the mass. At the top, potential energy is maximum and kinetic energy is zero. On reaching the ground, kinetic energy is maximum and potential energy is zero. Sum of kinetic energy and potential energy is constant and energy is conserved if energy lost to surroundings due to friction is not considered. Here you can see at the top potential energy is mgh and kinetic energy is zero because at the top it possesses maximum height and there is no velocity. But in the middle it possesses both kinetic energy and potential energy. When it reaches the ground, the velocity is maximum. So kinetic energy is half mv square, which is also equal to mgh at the top, and potential energy is zero. Kinetic energy and potential energy in pendulum. You can see a simple pendulum. The ball is oscillating. There are three different positions. One is the equilibrium position at the point A and the extreme positions at the point C and B. At the point C and at the point B, the ball possesses maximum potential energy due to a height h. But at that point, the kinetic energy is zero because the ball is not moving at that point. But at the point A, the ball possesses maximum velocity. So there will be some kinetic energy and kinetic energy is maximum. But the height is almost zero, so there is no potential energy. But between the point A and C or between A and B, the ball possesses potential energy and kinetic energy. But throughout the oscillation of the pendulum, the sum of kinetic energy and potential energy is constant. Energy measurements. Work. Work is done when a force moves. Work is equal to force into distance moved in the direction of force. That is, W is equal to force into distance. The unit of work is the joule. It is the work done when a force of 1 Newton moves through 1 meter. So to find out the energy possessed by an object, we can measure the work done. The work done will be equal to the initial energy possessed by the object. We can also measure energy during energy transfer. In an energy transfer, work is done. The work done is a measure of the amount of energy transferred. All forms of energy as well as work are measured in joules. Power. The power of a device is the work it does per second. That is, the rate at which it does work. This is the same as the rate at which it transfers energy from one form to another. So therefore, power is equal to work done divided by time taken, or power is equal to energy transfer divided by time taken. The unit of power is the watt. 1 watt equals 1 joule per second. Larger units are the kilowatt and the megawatt. Work, power, and energy transfers are related to our daily life. Here is one example: driving and car safety, braking distance and speed. For a car moving with speed v, the brakes must be applied over a braking distance s to bring the car to rest. The braking distance is directly proportional to the square of the speed. Thinking distance depends on the driver's reaction time. This will vary with factors such as the driver's degree of tiredness, use of alcohol or drugs, eyesight, and the visibility of the hazard. The thinking distance, that is the distance traveled while the driver is reacting before applying the brakes, has to be added to the braking distance to obtain the overall stopping distance. In other words, stopping distance equals thinking distance plus braking distance. If you like this video, please subscribe and share. If you have any question or suggestions, type in the chat section. Thank you.